So this lecture is about nuclear desalination, and it's more about actually to be informative, and it's to increase the awareness about the nuclear desalination, because usually nuclear power plants or nuclear energy is one part, desalination is another part, and the combination of both of them it's already exists, but not a lot of people know about it, and a lot of people have concerns about it. So we'll try to clarify everything through this lecture. I put a lot of slides together, and I collected them through many months and years, actually. So I'm not gonna cover all the slides. Depends on the time. If I see the time is passing fast, I'll go faster with the slides. However, you have the questions and answers, and after the lecture, you can call me or contact me anytime if you have further questions or if you need any explanation. Without any further ado, I'll go ahead with the lecture. So this is a quick outline. It's a quick introduction. We are going to talk overall and generally about desalination and Kuwait's heritage in desalination and nuclear energy with large nuclear power plants and small modular reactors, which is the future of nuclear energy and power plants. And then about the nuclear desalination cogeneration. A quick talk about my background is, if you can see from my work experience, at the moment I work at Kuwait Institute for Scientific Research, and this lecture is from my personal opinion. It doesn't represent Kuwait Institute for Scientific Research or the Kuwait state. That's my personal opinions. Because nuclear topic is very sensitive. So a quick work experience. I worked in Rhode Island Nuclear Research Reactor as an operator with experience of more than 100 hours of operation. A graduate research fellow in Oak Ridge National Lab in 2018 and Argonne National Lab 2017, and in Korea for non-proliferation in 2017. This is just to give you a quick idea that is my background is in nuclear engineering, and this is why the main focus will be in nuclear engineering. Education, graduated from the US in nuclear engineering. I did a master in biomedical engineering in Germany. And here is my contact info for later on if you would like to contact me. Current projects I am working on is called Coordinated Research Projects with the International Atomic Energy Agency. And they put teams together from different countries. We work on different projects. The first project I am working currently in is the economic appraisal of small modular reactors as main scientific staff and role of a nuclear cogeneration within the context of sustainable development as secondary scientific investigator and technical evaluation and optimization of a nuclear renewable hybrid energy systems as chief scientific investigator with the IAEA, or the agency I would like to call it. Kuwait Institute for Scientific Research, if you don't know about it, it's one of the oldest research institutes in the Gulf states, established in 1967. And it was established with the Arabian Oil Company by Japan. And later on was by an Amiri decree, it was accountable under the Council of Ministers. It is mainly about applied research. So we don't focus on theoretical parts. For example, we don't have theoretical physics, but we have applications of, for example, nuclear techniques and so on. We have a lot of partnerships, and at the moment, actually, we are working on a partnership memorandum of understanding with KAUST. Hopefully it's going to be done maybe after this lecture, who knows. We have over 580 researchers with over 100 laboratories across 9 locations. We have 4 centers, Petroleum Research Center, of course, and Water Research Center. They do a great research, especially in desalination and reverse osmosis. And we have the Environment and Life Sciences Center, which I am part of it, and then Energy and Building Research Center. Just a moment, please. All right. So introduction, nuclear cogeneration is where a nuclear power plant or nuclear reactors are integrated with other systems. And it has some other non-electric applications, for example, to produce hydrogen, desalination, district heating, or industrial process. And it has proven to be efficient and environmentally attractive option, especially for considering energy transition now, which is a hot topic, and all the other countries are working aggressively in energy transition. So nuclear desalination is basically seawater desalination using a nuclear energy. So again, this presentation is about awareness of a nuclear desalination, which I believe will be of a great benefit for the Gulf countries, especially considering their dependencies on desalination for freshwater production and their commitment to net zero emission by 2050. And due to my background in the nuclear engineering, I'll go over desalination in general, and I'll be focusing more on the nuclear energy. So what is desalination? Desalination is the process of producing purified drinking water from saline water. How? By removing salts and minerals. That's how easy it is. The process can be used for both seawater and brackish water. Brackish water is, if you don't know the term, it's between seawater and fresh water, somewhere there. Meanwhile, it can also be used to produce ultra pure water for certain industrial applications, also for like pharmaceuticals or food processing industries. So why desalination? Desalination is simply utilized due to their unavailability of freshwater bodies nearby, or poor rainfall records, or difficulty of connecting pipelines from fresh water resources due to the cost or distance or topological terrain. And of course, no wonder that is one of the most freshwater shortages in the world is in the GCC countries. This is why desalination is very important for us. Speaking about seawater content, here you can see some of the elements in the seawater, and I would like, do you see my, Mr. Abdurrahman, if you're there, can you confirm to me if you see my mouse moving? Okay, if you don't respond, I'll assume you don't see. But from there, you can see uranium. So uranium is basically in the seawater. So the next time you go and you swim in the sea or the ocean, you know there is uranium around you. And it's perfectly fine. It's totally natural. There's nothing wrong with the uranium. It's all over the place. So what are the desalination technologies? This figure shows the classification of desalination technologies by energy input. From a nuclear engineer perspective, really it is either thermal or non-thermal. On the left side, which is we are most concerned with, is the MED, which is the multi-effect distillation, and the multi-stage flash distillation. And from the right side, mechanical energy is the reverse osmosis. Of course, this lecture is not only about desalination, so we are not going to be cover everything, only those three, which is the main concern with the nuclear energy. So in the thermal-based desalination, fresh water is basically produced via a phase change process. On the left side is the multi-effect distillation, and it is used to separate salts from water. These processes are characterized by a huge amount of energy required as heat, not as electricity, as heat. The conventional thermal desalination technologies will be discussed here is the multi-effect distillation and the multi-stage flash distillation. These are schematics of these processes, and to put it simply, the multi-stage flash on the right-hand side in the bottom was introduced in the early 1950s. It is based on the principle of distillation through multi-stage chambers, where the pressure is suddenly reduced at each successive stage. And most of conventional plants using this technology are usually from 10 to 30 stages at this time. And every stage there is a decrease in temperature of around 2 degrees. For the multi-effect, it is one of among the oldest technologies in desalination. And the MED system is composed of a number of preheaters, distillation units, and condensers. In general, the evaporation process of seawater occurs at the surface of the two bundles heated by the steam. The steam is condensing inside the tubes, and vapor is generated in each effect. And in the subsequent effect, the steam experiences a significant reduction at pressure and temperature. On the commercial scale, most of the MED plants are coupled thermally with a vapor compressor, known as MED TVC, which is beyond our scope of presentation. And due to many operational problems, such as scaling and the high capital operating expenditures, the presence of MED was limited compared to the multi-stage flash. So most of the technology used now is basically the MSF, multi-stage flash. And this is the reverse osmosis, and it shows the depiction of the process. On the top left side, you see the forward osmosis, and on B, you see the related retarded osmosis, and C, you see the zero flow, and D is the reverse osmosis. These are considered membrane-based desalination, and they are the preferred processes for producing fresh water. And this is due to several factors. It is efficient, easy to operate with a high efficiency, and it is based on the use of semi-permeable membranes through which desalinated water can diffuse through the concentrated solution under a driving force. This technology usually uses electrical processes, not heat as the other two technologies we discussed, the thermal ones. So, Kuwait's heritage in water desalination. Kuwait in 1951 became one of the first countries in the world to commission MED, multi-effect distillation, for drinking water production. The first plant was in Shuwaykh, if you see in the top. And in 1960, it was replaced with MSF. Now in Kuwait, we have 8 desalination plants, located, of course, all of them around the coast. If you see them on the red triangle, these are desalination plants. And if you see the wastewater treatment plants are nearby. Next, we have a population growth in Kuwait. If you see from the early 60s, all the way to 2020, now we are around 4.5 million people, and this comes with an increase demand for water and fresh water resources. So Kuwait is mainly getting water from desalination, and the distribution is 61%, and treated wastewater for example, agriculture and other purposes, 20%, and from groundwater, which is considered brackish water, only 19%. Here you can see the gross production and consumption of fresh water in Kuwait. If you see, basically the consumption and production of water is almost similar, and it's increasing every year. It means that we actually need to have more desalination plants, and we need more production of water, or else we cannot keep up with the demand. Here you can see, for example, on the third column, gross consumption in millions cubic meter per year. In 1999, 382, and in 2019 it's almost doubled with 730. However, per capita consumption in liters per day for person it went down from 485 to 420, and that means that the awareness campaigns for control of how we drink water and use water is paid its toll. So it's very successful, these awareness campaigns. If some people they think awareness campaigns are not useful, it's on the contrary, even the numbers are showing it. Here you can see most of the water in consumption in Kuwait is used mainly for domestic reasons, and the other 40% for agriculture, and for industrial reasons is only 6%. The potable water, potable is basically drinking water, is increasing every year, and now this is in 2016. It's around 600 billion liters, and I believe the numbers are even more at this moment. So the installed capacity of desalination plants in Kuwait, I told you we have 8 of them, and the latest one was commissioned in 2016. It's called Zor Shimali or Zor North, and we have the total installed capacity of almost 3 million cubic meters per day, and per year it's 717. Here we see the power generation and desalination capacities by station. This slide is basically to show you there's the technology they use, for example, steam turbines or combined gas turbines or gas turbines. And at the end we have Shigaya. If you see, it's a renewable project that uses solar and wind. However, it's not connected yet or not used for any desalination purposes. And as far as I know, there are no plans so far to consider that. Here you see we have some plans for construction of a new water desalinations. We have almost 4 new ones, and we are removing 2, and we're gonna renew 1. And by the way, just to let you know, MEWRE is the Ministry of Electricity and Water and Renewable. We have plans for construction of new power plants till 2040, and these are the plans you can see here: renewal and removal and construction. And the Khairan and Nuwaysib is actually a bit delayed. Here from the Energy Outlook, published by every 2 years by biannual by Kuwait Institute for Scientific Research, we see the energy outlook for 2040 with the projections. As far as of this moment, the building sector uses the most energy, and this is due to 70% of it comes from using air conditioning. However, interestingly, we have a lot of transport energy use, and it is predicted that by 2040, the transport will take over even the buildings. And if you can see here, desalination, the prediction is almost similar for the whole time. Although we are having a new desalination plants, however, because the other sectors are using more energy, per percent, desalination is not using a lot. Although for every power plant, they are using more. However, we consider that in the future, the desalination power plants will be more efficient. So this is the prediction why it's not going to be using more energy than as of this moment. Here you can see the water production by desalination technology in Kuwait. At this moment, 2019, we use the most is multi-stage flash desalination and a combination of multi-effect and reverse osmosis. It is predicted that reverse osmosis is going to be the most in the near future. And total energy demand by desalination is the most energy goes to actually multi-stage flash and less to reverse osmosis and multi-effect distillation. So thermal energy is used a lot for these technologies, and it will be the focus on it from the nuclear energy perspective. And also, if we predict that reverse osmosis is going to be increasing a lot in the future, which uses electrical processes, we have to consider that as well. So some of the challenges facing the water sector. We have a lot of challenges, as you can see here. And I believe some of them, or most of them, they apply to the GCC countries, because we have similar almost terrain, similar environment. And one of them, I put a highlight, is the greenhouse gas emissions. So the desalination plants are actually energy intensive, and it produces a lot of CO2. And if we ever want to meet the net zero emission by 2050, we have to focus on that. What else I can focus on? I'm not going to read everything for you. It's there. I'm not going to bore you with it, but an important one is improving the water utilization efficiency and reducing the high per capita consumption through, again, awareness campaigns. And we have to revisit the agriculture and food sufficiency strategy. And there has to be a lot of work on preserving the natural water resources, the groundwater. How to face these challenges? We have to modernize the desalination industry. We have to improve the dialogue between the research and executing agencies, for example, KISAR, Kuwait Institute for Scientific Research, and the Ministry of Electricity and Renewable. We have to establish an independent entity to be responsible for water management. It shouldn't be Ministry of Electricity and Water. It should be Ministry of Water. And we have to advocate for more private sector involvement in desalination plants management. Also, how to face this? We need environmental protection. Simple and effective engineering solutions are available and should be adopted, especially for brine disposal. And brine is basically the water comes from the end of the product from the desalination. So you put the seawater, you get fresh water, and there is the leftover is the brine. And this brine is usually deposed in the sea again. which increases the salinity of the Gulf Sea, actually. Also, how to face this challenge? I am of the idea is that we have to consider a nuclear desalination cogeneration. Quick remarks: power, energy generation, and food are the main industries dependent on water. So apart from water and food and energy, sustainability is also crucial for the development of any country. There are three pillars for the stability of any country: water security, food security, and energy security. And these are intermingled. So water security, food security, and energy security are linked together, and they are known now as the water, energy, and food security nexus. And they are specially applied to the Gulf State region. So I think we finished from desalination. We'll jump quickly into nuclear energy, and I have to go through the fundamentals of nuclear energy. So when I talk about nuclear energy, you have the basic idea of it, because there's a lot of confusion usually from it. We will start from the atom. On the left side, you see, for example, the helium. It has 2 protons. If you add another proton, it becomes lithium. If you add another, it becomes a different element. Basically, proton is responsible for the element part, and it is known as the atomic number, down as you see in the helium as 2. On the top is the mass number, which is the proton numbers plus the neutrons. And of course, you have orbiting the nucleus is the electron. On the right-hand side, you have the hydrogen, and we have what is called isotopes. It is basically the number of neutrons. It affects the isotopes. So for the hydrogen, protonium, if you add 1 neutron, it becomes deuterium. As you know, with hydrogen, if it's combined with oxygen, you have water. With deuterium, you have heavy water, which that in principle will come later when we talk about the nuclear reactors. Tritium, on the other hand, you add 2 neutrons to it, and at this moment, the element, it becomes unstable, and it releases radioactivity. So again, this is the periodic table. All you need is hydrogen. You add another proton to it. You have helium, another proton, lithium, and you go so on till number 92, uranium. And after number 92, neptunium, plutonium, these are all man-made elements. They don't exist in nature. And here, for when the nucleus is unstable, it releases radioactivity, and there are 2 parts of radiation. There are charged and uncharged. Charged is, for example, electrons and protons or alphas. Uncharged is like gamma and neutrons. So alpha particles and beta particles can be stopped by a thin layer of sheet or even paper, while X-rays can go through a lot. They can even go through aluminum. And neutrons, because it's very neutral, it goes through a lot, and sometimes it even passes concrete. But with concrete, with enough thickness, it's enough to stop it. So what is the nuclear energy? It's basically the energy released during fission of the nucleus. So what is fission? Is basically when you have a neutron hitting the atom, it becomes unstable, and when it becomes unstable, it fissions, it splits, it releases energy, as you can see here, energy released, and you have 2 elements or fission products, and you have 3 other neutrons or 2 neutrons, and those, they go ahead and they hit another atom, and then it became like a chain reaction. So you keep getting a lot and a lot, and this is uncontrolled chain reaction. The energy released is a lot. It's 200 mega electron volt, and of all the energy, everything is recovered in the nuclear reactor, only the antineutrinos with 9 MeV. I think I'm getting short in time, so I'll go faster. So this is what I called the binding energy. On the top, you see the iron. Iron is the most stable element, as if every element somehow, this is an analogy, is trying to be an iron, to be stable. So hydrogen on the left side, in order to go above the ladder or the graph, it has to fuse. While the heavy elements, if you see on the right-hand side, like uranium, radium, in order to go to be stable all the way to iron, it has to split, which is to fission. When they fission, based on the probability, they usually go for these fission products from atom numbers from 80 to 160, and most of them is barium and krypton or xenon. So you don't have gold from the fission because the probability is very low or non-existent. So why nuclear energy also? This is an example of a small fuel pellet inside a fuel rod. It's almost like the size of a coin. This small pellet is the equivalent of 3 barrels of oil and 1,000 kilograms of coal and 17,000 cubic feet of natural gas. One small fuel pellet of uranium, it has that much of energy. That's how energy density is very important when you consider which technology you want to use. So why nuclear energy? As security, energy security, and we have volatile fuel prices, and we have a demand for a clean energy, and because of a climate change. Here you can see that the greenhouse emissions in a nuclear, if you see in the yellow, it's one of the lowest compared to all other technologies. So this is a very, very, very clean energy. And if you want to really go for to meet net zero emissions, you have to consider nuclear energy. A quick example: a 1,000 megawatt electric. For a nuclear, you need only 3 kilometers squares, while for the same amount you need almost 200 square kilometers. While with the wind, you need almost 900 or 1,000 square kilometers to produce the same amount of energy. So in case of Kuwait, there is a limit of how much you can go with solar. We cannot depend only on solar. You have to have a nuclear and other energy sources in the mix. This is also again about how important it is to consider a nuclear to meet net zero emissions. From here is the most important part. From all the meetings, conferences I have been to, from the books I read and so on, and studies, I didn't see any single realistic scenario to meet the net zero emission by 2050 without the use of a nuclear energy. International Energy Agency put it nicely: without additional nuclear, the clean energy transition becomes more difficult and more expensive. Here is an interesting, just in the last few days in the COP, 22 countries, they signed an initiative to triple in nuclear energy by 2050. So this is a great news for those involved in the nuclear energy. Here, let me see if I have to cover this one. So at this moment, the most energy resource used in the world is actually coal. I always thought it's oil, but apparently it's coal. And nuclear is only 10% in the world. Solar and wind and other renewables are 10%. However, they will be increasing heavily and faster. France is on the left side. You see France is the most country that uses nuclear energy, and 60%, almost 70% actually, of its energy comes from nuclear energy. And the United States has the most reactors in the world. I think short on time, I'll pass. I hope by now I convinced you that nuclear energy is basically should be considered in the energy mix. It has long commitment of 100 years, so a country has to really think about it when they commit to nuclear energy. This is a layout of a nuclear power plant. On the left side, you have the containment building with a nuclear reactor. And then you have the whole life cycle of a typical power plant. You have the condenser, the turbine, the generator, and then connected to the electricity grid. So if you remove the containment building and you put another energy resources, such as coal or gas fired, it's the same cycle. You produce steam, and the steam moves the turbine, and the turbine goes to the movement goes to the generator, and you have electricity, and the electricity goes to the electrical grid. And this is a live picture of a nuclear power plant. So what is inside a nuclear reactor? It's fuel pellets, the small ones I showed you. And then you have the fuel inside a fuel rod, and the fuel rod goes inside what is called a fuel assembly, and the fuel assembly goes inside the nuclear reactor, if you see on the right-hand side. There are many types of nuclear reactors, and a lot of them, they can be categorized by coolant. And the most important part for our purposes in this lecture is the water-cooled reactors, if you see, and they usually use very high pressure. Very short on time. I can pass this. And here is the enrichment of nuclear reactors. A lot of people mistakenly, they think that a nuclear reactor can explode. It cannot. And even if you tried, there is no way, because it only melts. That's an accident. The natural one of uranium-235 is 0.7%, and if you needed to put it in a nuclear reactor, usually it's you enrich it to 3 to 5%. And for research reactors or advanced reactors, it goes all the way to 20%. Above the 20% is not considered good, and it's considered high enrichment. Above 90% is used for nuclear weapons. There are generation 1, the old nuclear reactors, and generation 2, still old. And nowadays we have generation 3, including small modular reactors, and the advanced reactors, supposedly we have them within the next decade, is called generation 4. Most of the reactors used to produce electricity are called pressurized water reactor, and then boiling water reactor. So with the most experience we have with the nuclear energy is actually through the use of a pressurized water reactor. If GCC countries, they want to really consider advanced reactors, they should consider at least those that we have well-established technology, such as the pressurized water reactor. A quick example of pressurized water reactor is you have the containment building, the nuclear reactor. You have what is considered the primary loop, you see in the orange, connected with the pressurizer, and then you have the secondary loop. And this is good to consider, and this is why a lot of use of a pressurized water reactor, especially if you want to consider desalination, is that these are not connected. So if there is a leak in a nuclear reactor and a leak of radioactivity, it doesn't go to the secondary coolant. and it doesn't contaminate. Maybe we have at the end desalination or other purposes, other applications. This is the boiling reactor. It has only one loop. If there's a leakage, you have radioactivity can contaminate the turbine, the condenser, and everything. So this one shouldn't be considered for desalination. This is a CANDU reactor, and since we are late, I'll go ahead. This is a pressurized water reactor plant layout. You have the nuclear reactor there and the turbine connected to the turbine. The main control room on the left side is the old one, and the modern days we have the digitized one. The construction of or the project life cycle of a nuclear power plant can take all the way up to 100 years. The first 10 years is for the construction, and the most of the money goes into this part. The operation of the nuclear reactor for 60 to 80 years is considered cheap, and the fuel prices is considered cheap in comparison with the other ones, and they are stable. Small modular reactors is basically what we saw, however, in a smaller size. Small in size, modular because it can be built and fabricated in a factory and move to wherever you want. So you can order one exactly as you like from energy point of view and from features. And it's up to 300 megawatt electric. Why they are considered small modular reactors good? It's cheaper than larger ones because of the modularization. We said it can be fabricated in other in the factory, and the flexibility and smaller footprint. And replacement is considered in Europe and in the US replacement for aging fossil-fired plants. We can go ahead here. This is an example of a global SMR development around the world, small modular reactors. Saudi Arabia, mashallah, they considered a smart reactor, but I think that project is on hold, and hopefully they get involved in another. That was a project with Korea. If you want more information about SMRs, you can go for SMR booklet by the agency, International Atomic Energy Agency. And there you can download, and you see there is almost 83 new small modular reactor designs there. And it's biannual publication. These are some of the companies. I'll go ahead with this because we almost have only 15 minutes. Don't worry, if you need any of these informations, I can share with you later on. Just email me or contact me. These are all types of these SMRs, but let's go to the nuclear generation, cogeneration. So nuclear desalination cogeneration is basically you have the nuclear reactor here, which produces heat, and that heat can be used even for hydrogen production or direct air capture, or for our purposes, desalination. At the same moment, it can be used for producing electricity. This is why it's called cogeneration. You can use it for 2 purposes or even 3 or 4 purposes. Why it's nuclear cogeneration? Because most of the nuclear reactors are like 30 to 35% efficiency. That's for producing electricity, and the thermal heat is wasted. So if we actually use the thermal heat, for example, for desalination, the energy efficiency can be increased all the way to 80% and maybe even higher. It's more flexible. For example, especially small modular reactors are really good for the GCC because we have smaller grids, and 300 megawatt electric is very good in the case of Kuwait. We usually don't want to consider 1,000 or 1,500 because you need a lot of infrastructure for that. So SMR for small modular reactors for non-electric applications. If you see the ones we consider, the pressurized water reactors and the boiling water reactors, is called water-cooled reactors. They usually give you low temperature, and this low temperature can be used in applications such as district heating in Europe. We don't need this district heating. And however, we need seawater desalination, which uses almost 80 to 150 degrees. So this is a perfect fit, small modular reactors with water-cooled technology. The thermal energy from the small modular reactors can be directly used for the multi-stage flash and the multiple effect distillation, while the electricity can be used for the reverse osmosis. In the case of MED, it's easier maintenance and pre-treatment, and because it has high industrial quality water. For reverse osmosis, it's more efficient, increased availability, and low loss of power. It's more efficient, basically. So here is an example of these technologies coupled with a nuclear technology. In the case of the first one, reverse osmosis is electrical coupling with a nuclear reactor, where the pumping of feed water using a nuclear electricity and feed water can be drawn from the warm water outlet of final condenser, and indicating a small degree of thermal coupling. In the case of multi-stage flash, the thermal coupling with secondary steam cycle of a nuclear power plant, it has to be through an isolation loop due to the, I told you, the concern of radioactivity leakage. And typically steam at 10 bars with the 180 degrees extracted from high turbine pressure. Here is to show you that actually nuclear desalination exists. It happened. We have experience with it. It's not just an idea. Kazakhstan used it with a fast breeder reactor for almost 27 years, and they closed it down, and it used to produce 80,000 cubic meters per day of potable water. Japan also used it, and it's coupled to two pressurized water reactors and yielded around 14,000 cubic meters per day of potable water. And India is developing this technology, and Republic of Korea is considering their smart small modular reactor to actually be coupled with a mid desalination unit. So coupling between nuclear reactors and desalination units, there are aspects to be considered for coupling. One is safety, and then the site of the reactor. So for example, if it was in Riyadh, if we assume in a big city, Kuwait is mostly on the coast, it's not an easy task to put a nuclear power plant next to desalination, next to a big city where there's a lot of population. So this is why small modular reactors are better fit in this case. And since there are in our region, several countries are interested in nuclear desalination to satisfy their water needs, including Kuwait, United Arab Emirates, and of course Saudi Arabia, desalination in these countries have become a major concern. And a lot of studies trigger to evaluate the feasibility of these options. And these feasibility studies, they came to agree that it is cost effective, and it produces a clean energy, no greenhouse gas emissions. This is where I wanted to tell you about safety. So when you consider coupling desalination with a nuclear, you have to put intermediate steps between the steam and the condenser, and the steam coming from the turbine. So here is an example of coupling of multi-stage flash with a nuclear reactor. So you have a nuclear reactor on the left side, the steam generator goes to the turbine, you take all the way to the condenser, and from the condenser through intermediate heat exchanger, it goes to the multi-stage flash. Here is the safety aspect. If you put more safety barriers, you can separate them and you can be 100% there is no leakage of radioactivity or tritium, for example. And there is another example of MED coupling with a nuclear power plant. And here, if you see, also it goes through the condenser, the main aspect. And in this case, you don't need to use heat exchangers. In the multi-stage flash, you go back, you need heat exchangers, but a lot of studies, they saw that is more efficient if you use heat pipes, and it's gonna eliminate actually the probability of any contamination from radioactivity. And here is an example of reverse osmosis coupled with a nuclear reactor. And if you see from the top, from the electricity generated, it goes to the booster pump and to the high pressure pump for the electrical processes that is used by the reverse osmosis technology. We have a couple of minutes, and I think this one. And this is an example which is from feasibility studies and cost effectiveness. It was actually the best. It is the coupling of a nuclear reactor with MED, multi-effect distillation, with the reverse osmosis. So in this figure, you see that from this purpose is to generate electricity, the electricity to power the reverse osmosis, and also to power the desalination plant. And the waste heat from the nuclear reactor is used to produce steam that will be fed in the MED or multi-effect distillation. This is so far from feasibility studies is the best coupling schematic. More studies have to come, and I think in this case maybe a combination even with the MSF would be great. In the future we might have the forward osmosis more applied. So there is a lot of research to be done here, and I hope I showed you that at least this technology that in nuclear power is already used with desalination with no concerns at all. So what are the main challenges? It's actually the public acceptance. And I think this can be solved through awareness campaigns, like I showed you in the case of water. Why public acceptance? I just give you an example. A lot of food now is irradiated with X-rays or gamma rays to kill the bacteria, and this is the safest type of food you can have. However, a lot of people are scared that is treated by irradiation, and it is perfectly safe, but people reject that type of food. So maybe this is an issue also with desalination. People would think, oh, this water is treated with a nuclear and there is radioactivity, so they wouldn't consider drinking it. So a lot of awareness has to accompany this from the beginning, from engaging the stakeholders and the public from the beginning of thinking of this project, if it is ever to be considered. And there is safety aspect. And I hope I showed that through using SMRs, rather than the large reactors, they have passive safety mechanisms. So we don't have any dangers or accidents as you have seen before, like Fukushima and Chernobyl. These SMRs are inherently safe and uses passive safety mechanisms. The chance of accident is almost almost zero, but there is nothing called zero. But in case something happen, it can be usually naturally. It uses forces like natural circulation or gravity to cool down the reactor. Let me see here. The major safety concern in the nuclear desalination plant are related to the nuclear reactor operation itself. So the desalination is concerned with the contamination of a fresh water by radioactive materials, while a careful design and assessment for the barriers between the plant streams should be performed for these nuclear desalination facilities. Conclusion, SMRs, as opposed to large reactors, is the safest option, especially for newcomer countries, like hopefully Saudi Arabia, inshallah, hopefully Kuwait, and already ahead of us is United Arab Emirates. And I believe the Gulf countries, in order to meet net zero emission by 2050, while also facing water shortages, really have to consider nuclear desalination in their upcoming strategies, along with other non-electric applications, for example, hydrogen production and heat process. These are some references and further readings. If you like, I can share with you, or you can take a screenshot. And thank you, and sorry for taking more time than I thought. I hope I covered a lot of information. If you have any questions, please feel free to ask.